Welcome, ladies and gentlemen, to episode 2 of this lecture series. Today we will be covering Kirchoff's voltage and current laws. For context, in 1845, a man by the name of Gustav Kirchoff, or Kirchoff, depending on how you want to pronounce it, I don't know the real pronunciation, took the work that we discussed previously, which was Ohm's law, and made a generalized solution to explain what's occurring. So George Ohm was less concerned about the actual physical phenomenon that's occurring inside of an electrical circuit. He was more interested in defining a mathematical relationship between voltage and current, which, as we see, is resistance. This V equals IR. So Kirchoff took that idea of a mathematical relationship and tried to apply it to a more generalized solution of all circuitry and all voltage and current phenomenon that we would see in everyday life. And a huge portion of this is actually the law of conservation of energy and mass. Kirchoff recognized that in chemical experiments, everything that you put in, all the mass that you put in, all the energy that you put in will come out of the chemical reaction in some manner. It would be maybe a different form of matter, but it would be the same mass and the same energy would come out of the reaction. And so what he does is he says, okay, it must be that when we're pumping current into a circuit, that current must go somewhere. And so Kirchoff is effectively saying that all of the current pushed into a system must come out of the system. And if you think about it logically, this kind of goes along with our analogy of water flowing through a river in last episode. So our river, of course, has a winding nature. It's not uniform. It has these weird eddies that produce a different kind of resistance to the current. But Kirchoff is saying that whatever current flows through the top of this channel must eventually flow through the bottom of the channel. And it makes sense because the water has to go somewhere. In our case, the charge has to go somewhere. Now, when we start talking about other devices like capacitors and inductors, and we start talking about active devices like diodes and transistors, these statements and these laws become a little more vague and ambiguous, but they always hold true. And what we develop, so if we take George Ohm's circuit that he was experimenting with, he had a thermocouple here that was just outputting a voltage related to temperature. And then he modeled a small constant resistance coming out of the thermocouple. And then he actually experimentally generated a larger resistance by changing the lengths of cable connecting the two sides of the thermocouple. Now, funny enough, something that I realized in my researching and trying to figure out how to explain this, George Ohm just kind of assumed that this was the case, or at least he didn't even write about it, that whatever he's pumping through this thermocouple into the circuit would actually come back. He just kind of assumed that whatever voltage this thermocouple generates between its two nodes here and here would have to equate to whatever voltage is left in the circuit. There was no idea that maybe some sort of charge would be reactively held inside of the cable, which is something that we'll get to when we start talking about inductors and capacitors. And so what Kirchoff says is, okay, so we've got this voltage that's generated by the thermocouple, and then we have these voltage drops, in this case V little r, across this resistor, and then a big V times big, or I'm sorry, a big VR across this second resistor. Kirchoff would say that if we measured the voltage drop between this node and this node, that would be VR, or V little r, and then this node and the bottom node, that would be V big R. If we summed those two, so that would be VT equals V little r plus VR. And And it kind of makes sense because, once again, the current has to flow somewhere. So if you think about the current coming out of the thermocouple through this first resistor, it's passing through this particular node. Well, if it's coming into the node, it has to exit the node somewhere. The only way it can exit is back through this little resistance. So suddenly that's how you generate V little r. So that's going to be I forgot how to draw there for a second, times little r. Well, that current that's passing through the little r must pass into this node. Well, there's only one way for that current to continue flowing, and that's through the big resistor. So that's how we develop a voltage drop across the big resistor. And so this is kind of where we get the idea of devices in series, in this case little r and big R. They must receive the same current. Now, there is a different scenario where what if we had these two resistors in what we call parallel? Well, suddenly whatever current is passing into this first node doesn't necessarily equal the current passing through both resistors, but importantly, it does equate to the current that passes through both nodes. So whatever comes into here on the left side must exit on the right, but between these branches it may be different. And so what Kirchoff's current law is stating is that all of the current entering a junction or a node, which we can just draw here, you've got a current here, you got a current here, you got a current here, and you got a current here. Well, in this one we have current A, we have current B, we have current C, and current D. They must equate to the current leaving the node. So that would be A plus B plus C equals D. Did I draw that right? I did draw that right. Okay. And then he's also stating with his voltage law that from the terminals of a voltage source, like we have here with the thermocouple, then every loop that we draw with that guy must equate to the voltage across that thermocouple. And an important thing to note about these voltage sources is that they are trying to maintain a voltage between these two nodes, their top node and their bottom node, their positive terminal and their negative terminal. And something that we'll see in much more complicated circuits that would become relevant when we get to dependent sources or even current sources or that sort of thing is the voltage source it will generate as much current as it has to in order to fulfill this condition, that you always have a stated voltage across those two terminals. So now that we've kind of gotten Kirchoff's law sort of out of the way, we haven't really done a great example of why we even care about these circuits and analyzing these circuits. And I think a great example that everyone can relate to is actually a light in your home. So there's three devices that we really care about for just a simple circuit concerning a light bulb and a light switch, such as the ceiling light in your living room or your bedroom, and then the light switch that controls that light. And that's the panel over here on the left, with its little circuit breaker that's rated for, let's say, 15 amps. And all that means is the circuit breaker is constantly measuring the current through both of its terminals, like it's acting like a voltage source. And then the moment that it exceeds, in this case, 15 amps for a prolonged period of time, for 5 seconds or 3 seconds or whatever it's rated for, then the circuit breaker will trip, it will open the circuit, and it will not allow current to flow. Then you have to go reset the breaker and flip the breaker back on, and then you can resume normal operation. But coming out of the coming out of the breaker directly, we have usually a black wire, what we call the hot wire, and it will attach to a gold screw terminal on your light switch here. So we would call this wire the hot, because if you touch it, you now become the path to ground, and you will be shocked. And then coming out of the top of the light switch, out of a silver screw, usually, we have what is considered the neutral. The neutral is less, it can still carry a current, so you have to be a little careful about what's going on here. Shrink that. Okay. So you have to be careful about touching the neutral. If you at any point are not, if your circuit is not grounded at any point, the neutral likely still has a voltage across it, which means that it can shock you. But generally, the neutral and the grounds are going to be tied together at the panel, especially whenever you get to like a transformer or any kind of high voltage switch yard. But coming out of the other side of the light, the wire is actually going to cross all the way down, and then it's going to hit the neutral bus bar on this panel. And this bus is going to extend all the way up the backside of the panel and attach to the backside of this little breaker right here. Let me just see if I can do some of that. So that is kind of our complete circuit. Now, in truth, there is a little grounding that's occurring here. So you have a little ground terminal here, you have a little ground terminal here. I'm just using green to denote that. And then usually either on the panel itself or on the bus bar, or depending on the type of panel, you will have another little ground screw. And what happens is inside of the box in your wall, these two grounds will get pigtailed, they'll get tied together. And then you'll have a little wire coming and attaching to that light switch. So now all of a sudden, all three of these devices are grounded together back to your source, and that prevents any kind of shock occurring. But if we're talking about a circuit, all we really need to worry about are the hot and the neutral, because that's where the current will flow during normal operation. So we can treat that breaker or that panel as a voltage source, which I'll draw as VG, just for simplicity's sake. Well, then we're going to hit this light that we have here. And the truth is, the light can be modeled with a resistor R, and then wow, that is a terrible drawing. And then a series inductor. The truth is, we have yet to get to inductors, so I'm just gonna kind of gloss over that one. All you need to know is that at steady state, an inductor looks like a resistor of zero value, of 0 ohm. So it's a short, is what we call it. And then that will pass through that single pole, single throw switch that we have here in our light switch. And suddenly this becomes our circuit, which we can redraw to have that little resistor so that there's less confusion maybe. And we'll draw it a little smaller because we want to be quick about this. So this becomes our new circuit that we're looking at. And so when the switch closes, if it's ideal, obviously it's not inside your household, but if the switch is ideal, then it too becomes a short. And so we just have VG and RL in series, and the current coming out of VG will be directly related to the drop across RL. And this takes us right back to Ohm's law. But what if we had a bunch of these lights in parallel, like they are in your household, or if you were crazy and even put a bunch of them in series? You know, what's going to happen? How would we even calculate the current through that device? Well, let's say that we had two in parallel. Let's say that we had two in parallel. This is gonna kind of cover Kirchoff's current law real quick, so we can show you what's going on. So once again, they can be modeled just as simple resistors, nothing too crazy. And I'm not so worried about their actual naming convention, but what we will see, just to foreshadow, is the current coming out of VG will be split between these two branches. And you're asking yourself, well, what's going on here? How do I even start analyzing the circuit? Well, from an elementary perspective, we first want to identify all of our nodes. So we only have 2 nodes in this circuit because all of the devices are in parallel. We've got node A and we've got node B. The second thing we want to identify are all of the loops around VG. So the first loop is just between VG and R1, and I always try to draw them clockwise just because it makes the most sense in my head. I've seen other people draw them counterclockwise. As long as you maintain the same direction of current flow for all of your analysis, you'll come out just fine. So this is going to be loop 1. This will be loop 2. Now, if you figured it out, how loops work, you'll know that there's actually a third loop that extends all the way around, and that covers VG and R2 specifically. So loop 1 is VG R1, which we can draw really quick. So VG is going to equal V1 across R1. And then this loop 2 is going to be that V1 equals V2. This is all using Kirchoff's voltage law, of course. And then loop 3 is that VG equals V2. Now, here's the really fancy thing about parallel devices is they have an equivalent voltage drop across them. And if you think back to Ohm's law, for any resistor, it will have a stated voltage across it, regardless of the circuit conditions around it. As long as there is a current. If there's no current, there's no voltage drop. And then if we look at the 2 nodes, so at node A, we have IG flowing in because it's flowing towards the resistors, and then we have I1 and I2 flowing out of node A. Well, that's going to be I1 plus I2. And then if we look at node B, you say, okay, well, we've got I1 and I2 flowing in, and then we have IG flowing out. And so what you gather here is, well, these 2 statements are identical. So one of these is irrelevant, and usually we tend to draw, in this case, node B as a reference, as ground, and so we don't really care for the second equation. And another thing is, so you've got 3 loops. Well, in truth, these are all kind of the same. But what you'll find in most of your circuit analysis is that you need one less loop equation than you really have. So we can just kind of strike that last one, VG equals V2, off the record. We don't care. So if we take this a little step further and we say, okay, so IG equals I1 plus I2, so we know that I1 is just going to be V1 over R1, and that's the same thing for I2. So we've got IG now equals V1 over R1. And an important thing, V1 equals V2, so we can just draw them the same. So V1 over R2 this time. And the more astute of you may have already guessed where this might be going. So now we can draw, okay, V1, and then we've got this 1 over R1 plus 1 over R2. I'm realizing that my handwriting is not great with this mouse. I might need to fix this up. And then we go, okay, so V1, if we wanted to calculate that voltage, is going to be IG divided by 1 over R1 plus 1 over R2. Now, this relationship here, and I'm going to do it in red, this little equality, this fraction, not equality, this, this fraction here is going to be very important. It's what we define as the parallel resistance equation. And really what it will boil down to, if you work it out, is going to be R1 times R2 over R1 plus R2. And you can get there from multiplying the whole thing by R1 R2 over R1 R2, and you can see where that math will lead you. So we can just kind of redraw our equation with that in mind. Well, here comes another question of, I know V1 now. How do I actually calculate I1? Well, we know that V1 once again equals I1 times R1, and we can set that equal to this new value relating the current through that device, or through the circuit, apologies. So we have R1, R2 over R1 plus R2, once again our parallel resistance equation. Well, if I want to calculate I1, I just divide by R1. So divide by R1, multiply all of this by 1 over R1, these cancel, and then look, R1 cancels, R1 cancels, and so we get to I1 equals IG times R2 over R1 plus R2. So I understand that this is all letters and it's all words, and it's all symbols, but you can see the relation here. I1, if R2 were to increase, well, I1 would increase. I1 is proportional to R2 over R1. This is a very important equation to understand here. This is what we call a current divider, if I can type. Because the current IG is being split between I1 and I2 according to R1 and R2's values. And we can similarly write that I2, through the same mathematical steps, would be equivalent to IG times R1 over R1 plus R2. Once again, I2 would be proportional to R1 over R2. And I mean, this makes sense. If you have your river, your main channel flowing, and then suddenly it branches into multiple branches, several, maybe just two in our case. Well, if this particular branch here on the right has a much greater resistance, we can call that R2, then this resistance over here on the left, we can call that R1. If R2 is much greater than R1, well, then suddenly the current that flows through R1, apologies, would be much greater than the current that flows through I2. And this, of course, all derives from Kirchoff's current law. Well, if we back up a little bit and we look at a different circuit example, I can show you another fascinating phenomenon that derives from Kirchoff's voltage law. So we have VG again, and then let's say that we had those lights, those light bulbs in series now. So we know that you've got IG here. Well, IG, like we discussed before with ohms, with the ohms circuit example, IG is going to flow through this resistor, which we can now label as RA, and then it'll flow also through RB. So we immediately know that IA is going to equal IB is going to equal IG. Welcome back, ladies and gentlemen. I realized after recording that my microphone wasn't recording half of the discussion on voltage dividers. So I'm just going to step back through the proof and hopefully I can stitch these videos together. Let me just do this and delete everything. Yeah, I'm still figuring out how to get all this to work, so just bear with me. Anyways, back to the topic. So, like we just talked about before this cutoff, hopefully if I can get everything to stitch right, the current flowing from VG, which is IG, is equivalent to the current through RA and RB. Like we discussed previously, when things are in series, they have the same current passing through them. So we build this relation that IA equals IB equals IG. And then suddenly, I guess I should delete that too because I haven't gotten there yet. And so we can obviously build the classic KVL relationship of VG equals VA plus VB. And if we go ahead and substitute their Ohm's law equivalencies in, we've got VG now equals IG times RA plus IG times RB. And then we can go one step further and actually add these two resistances together. So now we get to IG times RA plus RB. And then if we wanted to calculate for IG, we can just divide VG by RA plus IB. And so this kind of points out a pretty important understanding that the current coming out of the source, in this case VG, is dictated by the resistance that it sees in the circuit. So the total resistance, in our case, just RA plus RB, will decide the value of IG. Now, we will later get to what are called active devices, which are transistors and diodes and that sort of thing, that when they hit certain operating conditions, such as a voltage, then they will source a very specific current. So this understanding that resistance dictates current is only valid when we're talking about passive devices, such as resistors, inductors, capacitors. But we'll get to that in time. The important thing that I want to jump to is now, okay, so we know how to calculate IG. VG is probably known. RA is probably known. RB is probably known. How do we calculate VB, this drop across RB? Well, we know that VB, because IB equals IG, is going to be IG, not that, my bad, is going to be IG times RB. Apologies, I've got a meeting in a few minutes, and so I'm trying to wrap this up. So IG times RB is going to equate to VB, something that we kind of figured out here when we realized the currents were the same. Well, suddenly we can substitute this into this circuit now. So we say IG is going to equal to VB over RB equals to VG over RA plus RB. And you can probably gather exactly where I'm going with this. We just multiply by RB. So you get VB equals VG times RB over RA plus RB. And you say, well, hold on, this equation looks really similar to this equation. It even has kind of the same setup, the same idea of one resistor divided by two resistors. And you realize that this is now what we call a voltage divider. And understanding what a voltage divider is vitally important for circuit analysis moving forward. It's this idea that anytime that we have two elements in series, they have the same current, but they have different voltage drops across them. Whereas if they're in parallel, let me see if I can do that, they would have different currents passing through, but they would have the same voltage across them. Whoop, that's a negative. That's a, yeah, okay. So it's this understanding between series and parallel that becomes vitally important for understanding some circuit analysis. And from this equation, we can draw sort of the same proportionality, that VB is proportional to RB over RA. As RB increases, the voltage drop across VB increases. And then we say, okay, that must mean that VA is now proportional to RA over RB, with the same equation with just a few subscripts changed around. So that is a voltage divider. And we've already discussed a current divider. These are two of the most fundamental uses of resistors in analog circuit design and much larger circuits. And frankly, understanding these two concepts will push you forward pretty far in your general circuit analysis. So in today's video, we've gone over voltage dividers and current dividers. We've introduced nodes and junctions and loops and meshes, and we've sort of discussed this idea of Kirchoff's voltage and current laws, that whatever you're putting into a circuit must come out of the circuit, a la the law of conservation of energy and mass. And it all sort of relates back to Ohm's law in that V equals IR. So with that, next episode we will be expanding on Kirchoff's voltage and current laws. First, by discussing different types of sources, voltage and current, independent versus dependent, as well as introducing the idea of equivalent circuits that are a la Thevenin equivalent circuits and Norton equivalent circuits. So with that, thank you for tuning in to this episode of GM Bandwidth.